Okay, hello, this is Ali again, and I'm talking about association rules today. So let's talk about this. So association rule is a set of algorithms that enable you to find association between different items in your data set. For example, in a grocery store scenario, sometimes you want to know what items are sold together so that you can basically put those items together so when people pick up one item, they could easily pick up the other one as well. They don't want them to be chasing around the warehouse. So the for example, some of these examples are like if they purchase bread and milk together, then you want to put them maybe in aisles that are close to each other so they go and pick them quickly. Sometimes some companies do the other way, do it the other way around. For example, Costco, they put things that people buy, for example, milk at the end of the store so they could walk the whole store and buy other items that they do not need in order to buy milk. So this information is important for managers and store managers and also grocery stores. This is not the only example. There are more examples. For example, Amazon, like an online store, when you see customers who bought this item also bought this other item, or in Netflix, when you see that, well, this is the movie that I recommend to you because you actually watch another movie, or YouTube is suggesting something based on your previous history. So these are all examples of where association rules could be applied. So association rules basically helps you identify interesting patterns. So there are some patterns anyway, but interesting patterns are patterns that allow you to go from X to Y. So these are the connections that are given to you on a set of items. So the items are going to be in a set. That's the data structure that is used. And mostly this is used on transactional data. So one of the major use cases of this is market basket analysis, where you want to find association between different items that customers actually are buying. And again, this is not a predictive method. So this is more like an analytical method that you go and understand your data. And the definition of interesting, like what is an interesting pattern, is defined by your algorithm and what you want to do. So a priori is one of the eldest algorithms that is used for association rules. So there are many algorithms for this. One is a priori, which is going to be what we're going to talk about today. So it's an algorithm for mining frequent data item sets and for this for Boolean association rules. It uses actually a bottom-up approach. So it counts the item sets that are bought together in a transaction, and then it tries to find more and more interesting item sets. It's designed to operate on data set containing transactions. So transactions like, for example, grocery store transactions or any like a store that, or any like set of any company or store that records a set of items that are bought together or actions that have been done together in a single session. So possible transactional data sets are, for example, retail items that are purchased together, a set of tasks that is done in a single day, or a set of links that user click in a single session. These are all transactional data sets that could be used. And this is used over like item sets. So item sets are a set of discrete variables. So they're not continuous. It's like this item, that item, this movie, that movie, this task, that task. So it's not like a number or anything. We have the number of occurrences of those, but those items are just a part of a set. There are four common ways to measure this association, which we are going to talk about. One is the support, which is basically number of times that pattern or that item is has been seen in the in our item sets. Confidence, we'll talk about that, and lift and leverage. So the a priori algorithm itself has a set of steps. So this algorithm actually finds the frequent item sets that you can find in your data set. So we need to define a few things before we go forward. So what is a frequent item set? It's a set of item L that appears together often enough. For example, like milk and bread, they could be a frequent item set. So they're a set of two items. But formally, they should meet a minimum support criterion, which means they should have been occurred at least a certain number of times or percentage of the total purchases in order to be included and called a frequent item set. So we have these item sets, but in order to be a frequent item sets, they should have been occurred at least a number of times. So support is defined as the percentage of transactions, of the whole total transactions that contain the item set. So this shows how popular an item is, or how popular is the two groups of items are. And there we have a property, which is an interesting property, which is called a prior property. It tells us that any subset of a frequent item set is also frequent. For example, if milk and bread are frequent item sets, which means milk and bread has been bought for so many times in all transactions that there are frequent, then milk is also a frequent item set and bread is also a frequent item set. So there are a set of one items, but we could have frequent item sets of more than one, two, or three number of items. And any subset of that is also frequent, which is trivial somehow. Like it makes sense that if both of them are frequent, then each of them are also frequent. So it at least has the support of its superset. So because milk and bread are frequent item sets, then each of those are frequent as well. This is called the a priori property. So let's talk about an example. Consider a grocery store with 1,000 transactions. These are the total number of transactions which we use to find the frequent item sets. And we have these items, different items in the baskets of all people, like milk, bread, eggs, cookies, meat, and potatoes. And the minimum support that we define for a frequent item set is 50%. So an item or item set is a frequent item set if it appears in that 100 transactions that we've got, 1,000 transactions that we've got, at least 500 times, or 50% of those. So when you look at these frequent item sets in this table, we will see that milk has been occurred in 70% of the total transactions, bread in 81.3% of the total transactions, and milk and bread together, they have been in 62.7% of the transactions. So these are the frequent item sets. An item set could be of size 1 or more. So all of these are item sets. So we call them that they have minimal supports, and we can find some rules here. We could say that, well, if someone buys milk, then probably they buy bread as well, because these item sets have a good support. Or we could say if someone buys bread, they probably buy milk as well. But is it the same scenario that, like, can we really say that, well, if someone buys milk, they will buy bread? Or is it when they buy bread, they will buy milk? So that's something that we have to dig further into, because you can see that in general, like most people buy bread, but not all of them buy milk. So Maybe if they buy milk, they buy bread for sure, or like for any other reason. They may need bread anyways, but they may not want milk. So we can use another measure to find the significance of that threshold or support, and that is called the confidence measure. So confidence, well, let me go here. So confidence is defined as the percent of transactions that contain X that also contain Y. That's how we define the confidence. And in our algorithm, we want to find the rules that are actually have like a minimum support and also a minimum confidence. So we want to make sure that we are confident in that rule actually exists because of a reason. It's not just coincidence. It's that people who actually buy one of those items, they actually go and look for the other item. So the algorithm, the search space that we're looking for here is that, so we talked about this algorithm a few times. What we usually do to find these rules, these confidence rules, is that we start looking at the data set and creating item sets of size 1, so like milk and bread only. Then we'll start to combine them and try to see if we have milk and bread as well in there or not. So we grow the size of the item sets from 1 to k. K is the maximum number of size of the item sets, and or until we run out of support. Like if we don't have 5 items that are bought together 50% of the time, then we cannot create that 5 item data set, item set, five item sets. So a prior property lets us prune the data set, those transactions that do not contain the minimum support. And these frequent item sets that we create are used to after we found them, help us find rules in the form of X then Y that has a minimum confidence. So not only we should make sure that those items have a minimum support, but we should also make sure that we have confidence. I'll give you an example of that. So the output of the a priori algorithm is the set of all rules in the form of X then Y with minimum support and confidence. So you should have both minimum support and minimum confidence. So let's talk about some examples here. Again, in this same example that we have, like in the for the 100 records that we have, we can have the different, these are the different combinations. So in total, we have 1,000 like records. So in total, we have, for example, let's read this table first. We have 300 cookies that are bought, 700 milk that are bought. Like, I mean, they have been spotted, milk has been spotted in total 700 times of 1,000 times. Bread has been studied 813 times out of 1,000. Eggs are the same as well. So these are the transactions that we have. So, and we put them in this kind of neat table to find out how many times, for example, milk and bread actually were bought together. So when you look at this, from the total 813 times that bread was bought, 627 times of that milk was also bought. So this is how we could read this table. So now let's look at this and let's look at the confidence rules that we could find. So remember what the confidence rule was. So when we say X then Y, we say that from the total times that we had X in a transaction, how many times we also had Y. So first we need to get the total number of X and then find out how many times X and Y were bought together. So for example, if we're looking for milk then bread, milk is the X. So first we need to find how many times milk was bought. So if you look at the milk, the total number of times the milk was bought is 700. We put it there like in our formula, and then we find out how many times milk and bread were bought together, and that's 627 times. So we put that here. So in total, we have 89.57% confidence that when someone buys milk, they also buy bread, which is like almost 90%, which is also a very good confidence level. What about the other way around? Can we say that when people buy bread, they also buy milk? So when you look at it, so this is a rule of type this, X then Y, then first we find the total number of X. So the total number of X, which is bread, is 813. We put it there. So how many times milk and bread were bought together of the total 813 times 627? So when we calculate that, we'll see that these two rules, like although milk and bread were bought together like for so many times, which is a frequent item set, but the confidence that when milk is bought when bread is bought is actually 77%, and the confidence when we could say bread is bought because after someone buys a milk is like 90%. I just give you an example of why this could happen. I could say that bread is like more of a need. A lot of people might be like lactose intolerant, or they do not like dairy, or milk could be a little bit more expensive as well. So when someone forced to buy milk, they can afford to buy bread as well, and that's probably why most of them buy that. But not all people who just afford bread because that's a very basic need, they afford milk or they are interested in milk. That's why it's a little bit lower. So these two confidence measure actually tells you how what is the relationship between these two items are, and but this could be sometimes misleading because in general, like milk and bread is bought by a lot of people, and these ratios might exist just because they are like bought by many people, and there might not be an actual relationship between them. So we understood that we have some confidence that this rule exists, but we may want to know it's not based just on popularity. There is a relationship between milk and bread. That's what we're looking for. That's why we introduced another measure, which is called lift and leverage. So lift is a measure that tells you how important the relationship between the two items when they're bought together is over their independent support and their popularity. So if there is a relationship between them, which is kind of higher than their popularity, I could call this part popularity. If there is a relationship between them which is higher than their popularity, then we have a lift greater than 1, which means that item Y is likely to be bought if item X is what, which means relationship is interesting. But if their support or popularity is very high by itself and the relationship is not that important or not but together, the support after union is not very high, then we may have lift equal 1, which is there is no association between them. The relationship is coincidental, And if it's actually lower, it indicates that item Y is unlikely to be bought if item X is bought. So it's like they're the opposite way. Like they're popular, but no one buys them together. An example of that I could think of is maybe lactose-free milk and milk. So people buy milk a lot, but those who buy lactose-free milk, they may not buy milk, and vice versa, because you're either lactose-free, lactose intolerant, or you're not. Maybe some people buy it because of their family, like they just buy both types, but usually some people are maybe sensitive to one item. It's the same with maybe peanut. Like you either buy just regular peanut and then you buy some snacks that contain peanut, or you're allergic to peanut and don't buy anything at all. So some of these relationships are like in a way that support each other, or in a way that is like the opposite way. So Lyft tells us that, and you could calculate that and understand whether that relationship is actually an interesting relationship. If you want to get the difference, the leverage, how interesting that relationship is, then instead of just dividing them like together, you could just get the support minus the like support of these item sets minus their popularity. And it just tells you whether what's the difference between them. Okay. So an example is, for example, bicycle and helmets. So not a lot of people that go shopping, they go and buy bicycle and helmets from Walmart, for example. So they go there, like from the 10 times that they go and buy anything, they may buy milk and bread, but maybe once a year or twice a year or once in many years they buy a bicycle. But when they buy a bicycle, there's a high chance they actually buy a helmet as well. So this relationship is a very interesting relationship. So bicycle and helmets are bought together. There's a high support for both of them, but there's a very low support for each of them individually. So the lift here is going to be a very high lift because there's an interesting relationship between them. What about lactose-free milk and regular milk? They have a very high support. Both of them are bought, I guess, frequently. Maybe one of them more. Regular milk is bought more, but lactose-free milk is also popular. A lot of people buy that. But when you look at it, I assume that, well, the support of both of them bought together is actually low, lower than their popularity, which creates a leverage, like a lift of less than 1, which means that their relationship is kind of a negative. So people who buy regular milk, they probably do not buy lactose-free milk, and people who buy lactose-free milk probably will not buy regular milk. So that is the relationship that you could find out. In our example, if you want to look at what we had, so if you want to calculate, so we had these confidence intervals there anyways, but if you want to calculate the lift of these rules, the lift of milk over bread, or like bread to milk, if you look at them, and it's the same thing, like x and y and x, like this relationship in general is what we're looking for. So this is the popularity of them. So how many times people buy milk, how many times they buy bread, and then that's the support of them. And what is the support of both of them? So this is what we put at the top. This is the kind of support of x and y, or basically support of milk and bread. And this is the individual support of them, support of x, as of support of x, and support of y, which we multiply that to get the lift. So when we look at the lift, we'll see that the lift is actually more than 1, which means that this relationship is actually interesting, and there's a relationship based on people who buy milk and bread. So just they buy together, not just random or because of like popularity of them. They buy it because there's a relationship. So people buy them actually together. So now let's talk about the actual algorithm that goes from the data set to the rules that are going to give us. So this is the a priori algorithm from the start to the end. So we start by creating, defining the LK, which is the set of frequent K item sets. K starts from 1, so L1 is a set of frequent 1 item sets. Let me give you an example of this. This is an example of L1. L1 is the set of items that they're just 1 items in each item set. So these are the frequent item sets of size 1. That's called, we call that. So first we create that from the data set and see, okay, how many times people bought bread, how many times people bought, I don't know, milk, and etc. But what we do is that we pick only frequent item sets, right? So frequent item sets are the item sets that have a minimum support. So this minimum support is basically those who have, for example, that's what we define, they have at least 50% support, or in the transactions at least 50%. So we create that LK, the first one, as a frequent K item set. Then we join that item set to itself. So because of the a priori property, if milk and bread are bought well enough, there is a probably milk and bread together are bought together as well. So we create a candidate set by joining those items together, and that's a candidate for the next item sets. But we want to know if that's a frequent item set or not. So we prune out those items in that candidate item set that do not have the minimum support, and then voila, we have the frequent item sets of K plus 1. So basically, in other words, we find out the items that are frequent. We try to create items of size K plus 1, like if you have item sets of 1, we create item sets of size 2 and find out if they are also frequent. And if they're frequent, then we have the frequent item set of size LK plus 1. So, and this works because of the a priori property, because we know they have minimum support, there's a chance that they have their combination also have minimum support, and we do not miss any frequent item sets, because if there's some item sets that is not present in the original, like one item set that we had, there cannot be anything there, because each of those items, so like each of those individual items in, for example, the L1, none of them exist in that item set of size 2 or 3. For example, we cannot, when we have, let's talk about here. Let me give you an example. If we have bread, milk, soda, and potatoes, which are frequent 1 item sets, then it's impossible to have bicycle and it's impossible to have bicycle and helmet as a frequent item set, because bicycle is not a frequent item set itself, and helmet is not a frequent item set as well. So it's impossible to have something like that. Because of that, instead of looking at all different combinations of items that we have, we just only look at the ones that are already frequent and start building from there. So that's what we do next. So we create that, and we continue until we reach the K of maximum, like we have item sets of size 5, or we run out of support, which is the likely case. Then at the end, what we do is we get the union of all the rules that we have found, like all of the LKs that we have, all the frequent item sets, and find only those that have the minimum confidence, because we could have a lot of different rules and different items, but we're looking for those rules of type X then Y. That's what we're interested in, right? We're looking for those rules of type X then Y that have a minimum confidence as well as minimum support. So, okay. So let's give you an example. So this is where the algorithm starts. So we set the minimum support to like 0.5, and we have 100 transactions. So we scan the database and prune any transaction that is less than 0.5. So from 1,000 items, you will see that these are the items that could make it to this stage, and this is the L1, which is the frequent item sets of size 1. So K is 1 here. Okay, so the next step is that we are going to kind of join these items together and create more frequent item sets. For example, we create milk and bread and milk, bread and soda, bread and potatoes, milk and soda, milk and potatoes, and soda and potatoes, and then count calculate their support and see if they meet the minimum support. So we join the L1 to itself, scan the database to get the actual counts, and then we pruned it. And what we have here is that we've got milk and soda was found together that were bought together 544 times out of 1,000, and milk and bread were bought 627 out of 1,000. So only these two rules made it to L2. So we continue this and we try to create the L3 data set, but excuse me, we run out of support because we do not have any for example, let's go and see what we have. So we've got milk, soda, and milk and bread. We go and try to find out if we have an item set that contains like milk. What is the support of milk, bread, and soda? So because milk and soda are already like 544, probably when 3 of them are bought together, it maybe goes under 500, becomes, I don't know, 450 or something. So it doesn't make it to the minimum support criteria and doesn't make it to the next round. Okay, so yeah. So we run out of support, and then these are the rules that we could create. So the rules are like milk, soda, soda and milk, milk and bread and milk. So because these were the frequent item sets, so the possible rules are one of these. So you see these two they came out of the relationship between milk and soda, and this came from bread and milk. So we calculate their confidence, and remember what confidence was. So the confidence of X then Y from XY is the percentage of transactions that contain X that also contain Y. So so for the relationship, if milk then soda, okay, which is milk then soda, okay. So if milk then soda, then first we need to know how many times we had milk. So we go and look at the support. So we had 400 milks there, and we put that there, and then we calculate the number of times that milk and soda were bought together, which is 544, and we divide 544 or 700, and it gives us the confidence of 77%. So we do the same for the other rules here, and you can see, for example, in the case of the bread, if bread then milk, how many times we had bread? 813. How many times we had bread and milk? 627, and this is the confidence we have. Yeah, I just have to check these numbers to make sure they match what we had before. So just calculate it and get it there. So then you have some rules, and that rule is going to say, well, if you want confidence, a confidence that is over 80%, that's the minimum confidence that we're looking for, then out of all these rules, only this rule make it. So we go all these steps, and then we're looking for the rules that not only meet the minimum support, but they also meet the minimum confidence, so that we could rely on and make a decision and make a huge change. So it seems like this rule of if soda then milk is something that is important. So people who buy soda, they're probably interested in drinks, and they buy milk as well. Anyways, so this is the this is how the algorithm kind of ends, and this is the only rule that we had at the end of a priori algorithm on this data set that gave us the rule that not only have the minimum support but also the minimum confidence. So if you want to diagnose this kind of this algorithm, you have to check, well, do the rules make sense? Sometimes it gives you some rules that may not make sense. So ask some expert and say, well, does this make sense? Sometimes it might be something they already know. It might be something obvious or coincidental. This is something that you have to talk with the experts. Also, you could test to see how your algorithm works. Make a test set from your holdout data and enter some market basket data and remove some of those items and see if your rules can actually put those items back in. So can your rule add soda or sorry, milk? Can your algorithm put milk in a transaction if it knows that they also bought soda? So if you remove some item and you just want to test your rule, see if it actually works and it could identify those items. And some of the test data may not cause a rule to fire because we just have a minimum amount of rules. There are some reasons to choose a priori and some cautions. The reasons to choose this algorithm is that it's very easy to implement, and it uses a very clear, clever way to prune your data sets using the a priori property. And it's easy to parallelize, like using MapReduce, you could just count the number of items easily and it can give you the results quite fast. And that's the case with these big data transactions data that we have. Usually we just want to count all these different things, and we use MapReduce algorithm. So the cons is that it requires many database scans. So like first it goes through items of size, like item sets of size 1, then it goes back to count the ones that contain both, and then it goes back and back. So it has an exponential time complexity. It could be better if you use, I don't know, somehow a dynamic programming or just count everything like one at a time. And it can mistakenly sometimes find some rules that do not make sense, and it should be like this can be identified by applying lift and leverage to make sure that actually there is a meaningful, interesting relationship between them. So I hope you liked this lecture, and if you had any questions, comment below or let me know. Okay, I used most of the content is coming from this book, so thank you for their great book. Thank you.